So now we are going to start with the Nernst equation, right. So first of all, you should know that why the Nernst equation is required. As we have already measured the electrode potential, like I told you that if we want to know about the electrode potential of any electrode, how we can know that? Just by connecting with the SHE. And we know that the electrode potential of the SHE is assumed to be 0. So you already know that how we can find the electrode potential of any unknown cell, that is just by the looking of the direction of the flow of electrons, and the value that we get in the voltmeter just indicate the electrode potential. So when we were finding the electrode potential relative to the SHE, at that time we took the concentration of the electrolyte as 1 molar, right. Keep in mind this because this forms an important base. What happened? See, when we were actually measuring the electrode potential with respect to SHE, we were taking the electrode potential of an electrolyte as 1 molar. But in real life, we will be taking 2 molar, we will be making 3 molar. So that means the concentration of the electrolyte can be anything, right. So at that time, what will be the electrode potential? How we are going to calculate the electrode potential in that case, right. So this equation actually help in that case. So whenever like you have the concentration of electrolyte not as 1 molar or other than 1 molar, there at that time actually you can know the electrode potential by using the Nernst equation. So just look at the board. So why it is required? I think you know that it is required to know electrode potential of electrode. It is required to know the electrode potential of electrode when concentration of electrolyte is not 1 molar, or you can say it is 2 molar, it is 3 molar, like that. So what happens in that case, that how you find the electrode potential? So for that I am considering a Daniell cell, because first we will be finding the electrode potential for the Daniell cell in which we are not having the 1 molar solutions in both the case. So we know that the cell is like this. We have ZnSO4, zinc rod dipped in it, and we have CuSO4, copper rod dipped in it, and they are connected by salt bridge. And moreover they are connected and there is a voltmeter like this, right. We have this kind of thing. So now what happens, as we know in Daniell cell, this undergoes the oxidation. That means it loses an electron and as a result release 2 electrons. And in this case copper actually gained electrons, that, or you can say it undergoes reduction and form the copper. This is what the reactions which are taking place in this container, that is in anode and at cathode. These are the reactions actually. So now like if I am going to look the electrode potential for this, so I am going to apply the Nernst equation for either of the half cell, because first I am going to find out the electrode potential of the half cell, then we will find the electrode potential for the complete cell, right. So let us consider this zinc beaker first. So now what is the Nernst equation? Like for this beaker, the general formula, or you can say general expression for the Nernst equation is E M in positive forming E naught, M forming M in positive, minus RT upon NF ln K. This is actually a general expression for the Nernst equation. So now I am going to apply this equation for this also and for this also. So that means if I write this this thing as this, so I will be writing like this way, minus RT upon NF ln K, right. So let us put the value for this thing ln, because we can change actually ln into log. So it is like this, value putting minus 2.303, because whenever you want to change ln into log, you have to multiply it, you have to put the value 2.303 as a prefix, and it becomes log now. You must be thinking that what are these values actually. So just keep in mind, this is the electrode potential for the half cell, total electrode potential. This is the standard electrode potential which we took with respect to SHE when the concentration was taken as 1 molar. This R is a gas constant whose value is 8.314 joule per Kelvin per mole. This T is temperature, that is 298 Kelvin. This N is number of electrons exchanged. That means number of electrons electrode is gaining or electrode is losing. F is Faraday constant, value is fixed 96500 coulomb, and K is nothing but equilibrium constant, whose expression can be written as concentration of product divided by concentration of reactant, and if they are moles you can just write the moles as the powers. So this is, I think it's clear, this is electrode potential for the half cell. This is the standard electrode potential when we consider the electrolyte concentration to be 1 molar, minus RT, R means gas constant, T means temperature, N means number of electrons exchanged, F is Faraday constant, Ln K, K is equilibrium constant. So if I apply this equation to this half cell, it becomes E Zn oblique Zn2 positive equal to E naught Zn oblique Zn2 positive minus RT upon Nf ln K. Right. So now I am going to change ln into log, and I know that if I want to change ln into log, I have to prefix the value 2.303. So this is what I am doing here is, this remain as such, this remain as such, I write minus again, remain minus 2.303 RT upon Nf log K, right. So now I can write again, I can further simplify the equation as, this is 2.303, R is 8.314, T is 298, F is 96500, N can be anything, right, and it is log K is concentration of product upon concentration of reactant. So these are my products, so obviously it is Zn2 positive, and this is my reactant, so that means Zn. There are no moles, so I am not putting any values here, right. So now how I can write this equation, I can write it as E Zn oblique Zn2 positive equal to E naught Zn oblique Zn2 positive minus, if I will solve this thing, these constant actually, I will get the value 0.0591. So you can either use this value or you can either use direct value of this. It is always convenient to use the direct value. So it is 0.0591, N remain as such, and log of Zn2 positive divided by the Zn. And we know that the concentration of pure reactant and pure product, or you can say concentration of pure solids and pure liquids are always taken as 1. So that means I can neglect it, or I can write 1 in place of this. So my equation becomes this, and even I can write the value for N, as I have seen that it is the exchange of 2 electrons here. So that means my N is nothing but 2. So this is how I can write the half cell expression for this beaker. Similarly, we can write for this beaker. So you can solve in the similar way, and you will get E Cu2 positive oblique Cu, E naught Cu2 positive oblique Cu minus 0.0591 as the constant, the product of our sum of all the constants which we use remains the same. Electrons involved again 2 log of product is Cu, reactant Cu2 positive, concentration of pure solid and liquid taken as 1, so this is 1. So this is my half cell reaction for this beaker. So now I am in a position to write the complete EMF of the cell. So complete EMF of the cell is E naught of the cell minus 0.0591 N log product minus reactant, product divided by reactant, right. So this is this. So I am going to put these, I am going to substitute these values into this. So before I do that, I will write the overall reaction which is involved in this cell. It is Cu plus Zn forms Zn plus Zn2 positive, because Cu2 positive has been reduced and zinc is being oxidized. So this is my overall reaction. So now if I substitute this value here, it becomes E cell is equal to, E naught cell is nothing but E cathode minus E anode. I am putting this naught indicating these are standard potentials, minus 0.0591. N is the total number of electrons which is involved. So the total number is 2 electron loss, 2 electron gain, so that means the exchanges of 2 electrons. Log of product is my this thing, I can neglect this factor actually. So I am left with Zn 2 positive. Divided by reactant, so I can write this as 1 because it is pure solid. So I am left with Cu 2 positive. So this is my E cell for the complete Nernst equation for the calculating E cell for the complete Daniell cell. So this is how you can do it. So what you need to know is just first see the electrode potential values, then look for that which electrode potential is going to, which electrode is going to show an oxidation and which is going to show a reduction, second step. And the third step, write the reactions involved. Fourth, write the half cell expression as I wrote, I just derived it. So you can also write directly as I told you in steps. So now as you know all this, so you can write directly as the expression same. So write the half cell expression for 1 beaker, half cell expression for 1 beaker, and then complete the calculate the E cell by taking this everything into the consideration. So this is how you are going to do that. And sometimes if you get like some if I'll show you one more reaction. Suppose I say that copper loses 2 electrons, there is a cell where copper loses 2 electrons and forms Cu 2 positive, and there is a cell in which Ag positive is getting reduced, right. So in this case you can see that it is losing 2 electrons and it is gaining 1 electron. So there, because you have to make it the total number of electrons as same. So I will, because here it is 2, here it is 1. So I will be multiplying this 2 here and 1 here. So that means this is multiplied by 2. So so that means in this case the total electron n is going to be again 2, because 2 electron lost, 2 electrons gained. And where you will write the expression for K, you will be writing the concentration of Ag raised to the respective moles, that is the 2. Right. So you need to keep this thing into mind, because if you will not square it or cube it, or if you won't write the moles, your question is going to be incorrect. So this is how you are going to do that. And sometimes if there is a question like if the aluminium, let us say there is a cell where aluminium is losing an electron forming Al3 positive, and oxygen is there which is gaining 2 electrons forming O2 negative. So here in this case 2 electrons here, 3 here. So you are multiplying this with 2 and you are multiplying this with 3, and overall n is going to be 6, because 3 into 2 is 6. So this you have to keep in mind, because you have to equalize the number of electrons as well. So this is the Nernst equation. So whenever you get a question like that, so just look at which electrode is going to undergo oxidation and which electrode is going to undergo reduction. Then write the half cell reactions, then write the overall reaction, and then just look for it that what kind of thing you are getting to solve in this case. And one more thing, if you have a Gibbs expression and if you need to find the E cell in terms of Gibbs, so how you do that? You find it by formula delta G is equal to NF E of cell. So that means you can find the Gibbs free energy change also by taking into consideration the electrode potential of the cell. So just use these things into numericals, the similar way you will have to do it. And like if I say one question like that, suppose I tell you that the electrode potential E naught for the zinc is let us say minus 0.76 and E naught for copper is plus 0.34, and you need to find this thing. So how you are going to do that? You are going to substitute the values, minus 0.76 minus same thing, and you need to find, and if there is concentration also given as something, just solve it with the log or anti-log and you will get the result. So this is how you have to perform the derivations, or you have to, there is a method to find the electrode potential by using the Nernst equation. And also keep in mind that this Nernst equation is applicable only where the electrolyte concentration is other than 1 molar. So this is what is the Nernst equation in order to find the electrode potential of the cell when the concentration is not 1 molar.